Mary Powell. I'm a postdoc fellow at Stanford, soon to be at AAP. And over the last several years, I've been measuring and analyzing AGN clustering measurements from X-ray surveys to learn about black hole growth. And so here I will show, the power axis would have for these measurements. And I'll just show some of the things we can learn from them. But first, I'll give a little bit of background and show, where we are currently. So in general, we'd like to understand how supermassive black holes grow and coevolve with their galaxies. And one way of studying this is by putting it in a larger cosmological context. So by investigating the connections between black holes and their host dark matter halos. This infers the larger scale environments of accreting supermassive black holes, and it can be probed through the spatial clustering of AGN. So several mechanisms that are thought to trigger AGN activity and black hole growth depend on environment. And so AGN clustering can test these various scenarios and provide complementary constraints on AGN fueling and feedback over time. So I'll just now introduce clustering studies and large scale structure. So here I'm showing snapshots from an n-body simulation of dark matter only, with time going to the right, where you can see that things get more clumpy as time goes on due to gravity growing the initial perturbations. And it's at the peaks of this density distribution where the dark matter halos collapse and form. So halos started out as initial overdensities that grew against the expanding universe. And after reaching a critical density, they collapsed and virialized into a bound structure. Halos grow hierarchically by merging with other halos and accreting mass. And it's at the centers of these dark matter halos where the baryons condense into galaxies at the bottoms of the gravitational potential wells that they form. So small dark matter halos may have 0 or 1 galaxy. The largest halos can have hundreds of galaxies, each within smaller subhalos. And so it's within this context how you can map the large-scale structure predicted from cosmology theory, which I'm showing on the left-hand panel, to galaxy distributions, which is what we observe on the right. And so by studying how galaxies cluster in space, or how they're spatially distributed, you can constrain their connection to their host dark matter halos. And the same can be done for AGN. So in principle, how AGN cluster on all scales just depends on two things: cosmology, which governs how dark matter halos cluster and how that evolves with time. And secondly, on galaxy and black hole formation evolution, which is ultimately what we want to learn about by making these measurements and assuming cosmology. So for dark matter halos, their clustering strength depends on mass to first order at a given redshift. So the box on the right shows a slice from a dark matter n-body simulation, where massive halos are shown in purple and less massive halos are shown in blue. So the left-hand plot shows the clustering strength on scales of 1 to 10 megaparsecs for each, where the more massive halos are more clustered, which you can kind of see by eye by their spatial distributions on the right. And so the amplitude of the AGN clustering strength on these scales can roughly tell you something about the typical halo mass that hosts the sample, as well as the overall environments of the AGN. But in general, there's actually a lot of information that can be gained by AGN clustering measurements. It can probe the scaling relations between AGN parameters and their halos. It can infer any kind of special or preferred environments of AGN activity, like cluster versus field environments. And since the growth and evolution of halos is well understood, clustering can be used to statistically connect lower redshift AGN to their progenitors in the earlier universe, which show how certain populations evolve over time. So it's a complementary and independent way of probing AGN fueling and feedback, without necessarily requiring all the detailed host galaxy information. So I'm just to briefly go over how clustering is measured. It's measured by the correlation function, which is noted by WP. This measures the excess probability that a pair of objects are separated by a given scale over a random distribution. So on the left-hand panel, I'm showing randomly distributed points whose correlation function is 0. And on the right, you can see that they're more clumped together. And so these points would have a non-zero correlation function. So in practice, for galaxy or AGN surveys, we make random catalogs that cover the full survey volume and sensitivity, and just count the normalized excess data pairs over this random sample. For galaxy and AGN correlation functions, there are two terms that dominate on different scales. So on larger scales, greater than about 1 megaparsec, is what is called the 2-halo term, which just measures the clustering of galaxies within the different and separate dark matter halos. And then on smaller scales, less than 1 megaparsec, the 1-halo term dominates, which measures the clustering within the same parent halo, so among the different subhalos or between the centrals and satellite galaxies within that halo. And this provides much more powerful constraints on how galaxies or AGN occupy their host dark matter halos, which is very informative for testing AGN fueling and feedback scenarios. So clustering on these 1-halo scales is what we'd really like to measure. But because AGN are rarer than galaxies, it's less often able to be measured with sufficient statistics. But one survey that it can be measured with is at redshift 0 with the SwiftBat survey. So that's what I'm showing here. This is full sky, shallow, hard X-ray survey. And in general, you can measure AGN clustering in two ways. You can measure the autocorrelation function, which counts just AGN-AGN pairs. But for much better statistics, you can cross-correlate with inactive galaxies, measuring AGN galaxy pairs, because there are many more of them, and they trace the same underlying large-scale structure. So cross-correlating with galaxies provides much better statistics than just the AGN autocorrelation function measurement. So this shows the cross-correlation function of this sample at redshift 0, and I recently used it to test the environmental dependence of AGN in the local universe and say something about the relationship between black hole mass and halo mass, which I'm showing on the right. And the ability to do this was mostly enabled by the 1-halo term. And while this provides useful boundary condition for models of black hole growth, it would be really great to be able to do the same kinds of things at higher redshift to see how these relations are established over time and to test whether environmental factors become more relevant for triggering AGN at higher redshifts. So here I'm showing previous measurements of AGN environments at higher redshift from using AGN from the Cosmos field, so either XMM or Chandra AGN data. The left two plots are clustering measurements, and while the 2-halo term is measured pretty well at these redshifts, there's less information on the smaller scales of the 1-halo term. And on the right is a plot also using Cosmos data showing another way of measuring AGN environments using local galaxy over densities. And the flatness of this plot shows that they didn't find any trends between the environment and the black hole accretion rate. But it would be great to be able to go further down in luminosity to reduce the error bars on these kinds of measurements, as well as look for trends across wider ranges of mass and accretion rate. So Axis should be able to do this. So in general, clustering statistics depend on the volume of the survey and on the space density of the AGN-AGN or AGN galaxy pairs. The planned intermediate survey should have sufficient volume to do clustering measurements and it would detect the less luminous AGN that Athena will miss, which are more numerous. And so by extrapolating my AGN-halo model and populating AGN in higher redshift dark matter simulations, I roughly estimated the kinds of clustering statistics that ACCESS will enable based on the planned intermediate survey volume and depth. So one caveat is that spectroscopic redshifts are really needed for these measurements. But fortunately, by the time ACCESS would fly, spectroscopic surveys like Euclid and Roman will have taken spectroscopic data in this redshift range, which is why I focused on it here. But I'm just assuming here that the AGN will all eventually have spectroscopic redshifts. So this plot here shows the fractional error of the correlation function as a function of scale. So lower on the plot is better, corresponding to better statistics. The black line is the current redshift 0 cross-correlation function measurement. Assuming the flux limits and the area of the intermediate survey, this is how well ACCESS will do. This is just the autocorrelation function of AGN alone, which is already better than the current redshift 0 measurement. But if you cross-correlate AGN with Roman galaxies, for example, this would be even better. So by making some rough assumptions about the Roman sample, this shows that ACCESS and Roman can provide, an order of magnitude better measurement than the best current, or one of the best current cross-correlation function measurements at redshift 0. So not only will the black hole mass halo mass relation be constrained at this redshift range, but the environmental dependence of AGN activity can also be explored. So this shows the cross-correlation function of ACCESS AGN in 4 different luminosity bins. And you can see that they're fairly well separated across most of the scales, or most of the bins. The model I used to make these predictions just assumed the same probability for AGN activity in all cosmic environments, where the higher luminosity AGN are more clustered since they're more likely to be in the higher mass systems. But if the Eddington ratio distribution or the accretion rates changed with environment, this trend would be different. So for example, if AGN activity is suppressed in massive halos, then you'd expect a suppression of clustering looking something like this. Or alternatively, if you assume that AGN activity is enhanced in halos that have recently accreted a lot of matter, or recently undergone mergers, then it would look something like this, again, where the ratios between each luminosity bin and their amplitudes would be noticeably different. So these kinds of clustering measurements with the luminosity function will be very powerful for testing models like this. Now, Athena will also do very well for AGN clustering measurements, since the survey is planned to be about 10 times larger in area. But because it won't go as deep, it will do better than ACCESS for the high luminosity regime, but not for the low to moderate AGN luminosity. So like 10 to the 41 to 10 to the 42, which are more numerous. So they will be very complementary in this regard. Another way ACCESS would be complementary to Athena is towards higher redshift. So now this plot shows predictions for redshift about 3, again showing the fractional error of the correlation function. Athena is shown by the orange dotted line, and ACCESS is shown by the blue dotted line, which would enable much better measurements for moderate luminosity AGN due to its smaller PSF. And so you see the orange line is very high, especially on the small scales, and ACCESS predictions in blue are much lower. So finally, I just want to mention that synergies between AXIS and JWST will also be very powerful for getting the close environments of high redshift AGN from observations of galaxy fields around AXIS AGN of varying luminosities. So while I don't have anything quantitative to say here, it will be possible to measure whether these high redshift AGN from both the intermediate and deep fields reside in overdensities or not for a very wide range of accretion rates and mass scales. So that's also another thing that will be very interesting. Okay, so that brings me to my summary. The clustering of AXIS AGN will probe the AGN-halo connection for low to moderate luminosity AGN at the peak epoch of black hole growth and earlier. It will probe down to host halo mass scales of about 10 to the 11 solar masses, which are progenitors of local AGN. An AXIS with either Euclid or Roman will provide much better measurements at redshifts about 1.4 than current surveys, enabling really precise luminosity dependent clustering on, especially on the small 1 halo scales, which will be really great for testing how the distribution of black hole accretion rates changes with large scale environment. Thank you.
Great. Yeah, please, you can either raise your hand or put questions in the chat. Nico actually has a question for you, Mary. What is the highest Z where we can measure clustering with AXIS?
That's a good question, and I haven't tested higher yet. I can look into that. I don't know the answer.
So one more general question. So I guess the reason, AXIS will be sort of better than the local survey is because you have so many more AGN. Like, is it basically that you have, 20,000 AGN, and so you can do a much tighter measurement? Is that correct?
Well, yeah, I mean, it goes much deeper, so we can do these measurements in many different redshift bins over cosmic time. And yeah, the ability for AXIS to probe down to the very lower luminosities at these moderate redshifts, that's not possible with any other instrument. So it'll be really great for that, because the lower luminosity AGN are more numerous. So and we don't really have many constraints currently on how those low luminosity AGN cluster at most redshifts.
Great. So now I'm not like totally current with the clustering field, but I know there was a lot of questions about whether obscured AGN sort of cluster differently. Is that still sort of an uncertainty? I know you had some results on low redshift, but what are people, and yeah. I guess sort of Eddington ratio is folded into that as well.
Yeah, right. So it's possible that the different clustering that's found between obscured and unobscured AGN is a selection effect. But it's still not fully understood, I don't think, because it's different in each survey, really. So especially if AXIS can, get the luminosity functions of both obscured and unobscured AGN at these redshifts, and if we, can measure the Eddington ratio distribution functions of each and sort of understand all the selection biases that go into selecting those, then yes, it'll be really great for testing whether or not the clustering differences between obscured and unobscured AGN are really because they reside in different environments, or just because of their selection and the different accretion rates. Yeah.
Okay, so there's another question from the chat from Arash. Basically, the sigma psi axis value of 0.3, is that equivalent to 3 sigma? That seems to be that seems low compared with the error bars of the cross correlation function.
Sorry, can you repeat the question?
Yeah, so it's one he posted in the chat about
Oh,
the sigma psi value of 0.3.
do you mean like what the units of these plots are? Oh, you're
Hello,
muted.
thank you for the great talk. Yes, that's the value I'm looking at.
Yeah, sorry, I should have explained this better. What this is so yeah, the error of the uncertainty of the projected correlation function divided by its uncertainty. So would it be, so basically for each scale it just sort of shows how precise you can get these measurements. Does that make sense? Sorry, I don't know if I fully understood the question.
We can discuss it offline. Thank you. I'll
Sure.
ask later. Thank you. No
Yeah.
problem.
So I'll ask one more sort of general question, since we have a couple more minutes. So, Axis will also look at a lot of these dual AGN, and I think from people outside the field, it's sometimes confusing, like where does clustering stop and sort of dual AGN and merger studies start, and how do you fold those two investigations?
Yeah, I think they're complementary. So, clustering probes larger scales than dual AGN. It looks at kind of the larger cosmic environments. But I think if more dual AGN were found, indicating that mergers do enhance AGN activity, then you would expect AGN to preferentially reside in certain larger scale environments as well. So basically, there's two different ways of testing that question. So the two different investigations are complementary in that way.
Okay, great. So if there are any more questions, maybe just post them in the chat and Mary can answer there. But let's switch over to Mark Reynolds talking about the galactic center and Sagittarius star.